lab tours in the afternoon and a public lecture in the evenings, and the organizers asked me to make an announcement that the meeting point for the lab tours and the groups that we are assigned to are all indicated on the workshop's webpage. Okay, so please take a look. And I think we are meeting at 1:25, yeah, 1:25 p.m. after lunch. And the meeting point is somewhere near the student union. So look at workshops webpage for the details. Okay, so our plenary talk today is given by Dmitry Pelinovsky, Dispersive Hydrodynamics in the modified KdV equation.
Good morning. I'd like to thank organizers not just for inviting me to the plenary lecture, but for keeping the momentum on dispersive hydrodynamics going. It's already the third meeting in 4 years' time. I remember the virtual meeting in 2021, the actual one program 2 years ago, and now the third one is quite it takes time to organize, I think, so congratulations. I will introduce some of my collaborators during the talk, but today, in the beginning, I would like to mention a single role of Markhofer in this project. It was very inspirational for us to think about the problems like this, and in fact, 2 years ago, we have solved some of the issues we had before, so it was quite a useful problem. My talk consists of 3 sections. In the first section, it will be just an overview results on the simplest possible problem of KdV equation. It's the introduction, but it's long. And then in the other 2 sections, I will talk about modified KdV equation. So for this first section, I would like you to pay attention for 2 particular things: stability of the traveling background, elliptic background, and connections to the existence of solid and propagating stably on this background, which we call bridges. But before that, I will start with a conventional slide. It appears in Panner's talk and Patrick's talk. The 2 coherent structures which arise in the Riemann problem with 2 boundary conditions being different from each other, constant background being different. In the first case, it is very effective, very sort of steady and slow and smooth. And the other one is a dispersive shock wave, which is a modulated traveling wave background, modulated elliptic background with modulated parameters. And this is something that's most important for us to consider. But I like to think about interactions of non-trivial solitary waves propagating along this background. And quite a good overview was published last year in Studies in Applied Mathematics, outlining 2 basic scenarios of interaction of a solitary wave and the coherent structures of rareifactive wave or dispersive shock waves. For the case of rareifactive wave, it's a solitary wave with sufficient large amplitude. It can completely overtake the rareifactive wave and appears with a steady speed, steady amplitude on the other side of the step and propagating steadily. And it's important to understand the amplitude, the speed, and the phase shift of this propagating solitary wave. And if the solitary wave has a sufficiently small amplitude, it gets completely absorbed inside of the rareifactive wave, never appears on the other side. It's so-called latent mechanism. The same thing happens when soliton interacts with dispersive shock wave. In the case of sufficiently large amplitude, it overtakes the dispersive shock wave, which is now been generated here from the initial step, and appears on the other side of the step and traveling smoothly and steady. But if the soliton has a small amplitude, then it goes trapped inside of the dispersive shock wave, and it never appears on the other side of the step, so it completely disappears, traveling mechanism. So since shock wave, dispersive shock wave is a modulated elliptic background, it's interesting to think if we can construct an exact solutions which describe the steady propagation of a solitary wave inside of this elliptic background with a constant modulus, with a constant parameter. And that's what Markov always called bridges. It's just soliton propagating on an elliptic background, but because of periodic interactions happening periodically in time, steadily in time, then he calls it bridges. And there are 2 particular different bridges for this problem. The bright bridges, when the solitary wave has large amplitude and it moves, as you can see from the picture, moves faster than the traveling wave. Every time it is connected with the maximum, will create a phase shift here, which is an important parameter for observations. Also, the localization width is another important parameter for observation for the solitary wave, as well as the speed. The speed has to be computed somehow, and it is not the same as the speed of a freely propagating solitary wave over constant background. So these are the characteristics we have been looking for. And in the other case, there is a dark breezes, which is just a depression soliton propagated inside of the periodic background. As we can see, it goes faster to the left, therefore if we count the speed together, it is going slower than the periodic wave. And the same thing happens that there is a phase shift, there is a speed. So here, the existence of such solutions and the existence of such interactions indicate background being stable from the point of stability analysis. Perturbations say that the background is not growing that. And with perturbation, traveling wave background is modulation is stable. And some applications of this will be just the connections of this right breezes with the first tunnel problem and that breezes with the second break. But what I was going to talk about that there is a connection between the existence of such breezes with the stability of the background. And if you look at the different models when the background is unstable, we will not anticipate the existence of such traveling periodic breezes, but instead we will anticipate the one set of modulation stability and creations of a completely different structures. And that's an example for the focusing on linear Schrödinger. In this case, both backgrounds, noidal and toroidals, are modulation unstable, and we can see the one set of modulation stability in creations of a rock wave, which is fully localized in space and time. And this rock wave can be thought to be peregrine solution, famous peregrine solution of constant background, but it is now sitting on the front angle elliptic background. That's fundamentals rock waves, second order rock waves, in fact, such solutions sitting on the background as the indications of instability. In fact, the amplitudes and magnification factors of these rock waves can be computed exactly if we have the exact solutions of the situation. And in fact, they can be observed in real life and in optics, in the group of figure, the observed formations of such rock waves in the propagations of light, and in the group of amines, who will speak after me. Here, George will describe of the breeder type rock wave solutions from modulation and stable monitoring. So the implications of both things. Solitons propagating steadily in the case of stable background and rock waves, which is one that due to modulation instability, is pretty obvious in physics, and therefore it's important to understand how we can actually construct the exact solutions in this problem. So here in an overview, I would like to say that I would like to consider traveling solutions, so it's not just elliptic solutions of the equations, but the full set of the traveling solutions, because from the point of applications, it's important to understand what's happening with the traveling solutions. And in the case of the KdV equation, we have a traveling wave profile satisfying pseudo-dot, which can be successfully integrated twice with two integration parameters here. So altogether, there are three important parameters in the system. It's a wave speed C and two artificial integration parameters B and D. However, the KdV equation has two important symmetries, the scaling transformation and the Galilean. And because of these transformations, one can reduce the set of all traveling wave solutions to the one parameter set. And in fact, the solutions can be generated in a very normalized way by means of Jacobi elliptic functions, C and squared. This is the only parameter available here to be elliptic modulus K, it's 0 and 1. All Jacobi elliptic functions are very nice, bounded functions, but also it's very nice interpolations between trigonometric functions. So we can think about Sn with sine, Cn with cosine. Dn and V1, the first three fundamental Fourier modes in Fourier series. In the case when elliptic models goes to zero, and we can think about hyperbolic functions, solitary waves, given the other limit. So this segment from 0 to 1 gives a one parameter family that the most general traveling wave solution can be obtained by using the scaling and gradient. Later on, there will be theory used here. So from the beginning, I was mentioned that these functions can be considered not only on the real line, which is important for application, but also in the complex plane, and they are double periodic functions, but the plane gives a period given by the fields. But from the point of our studies, we would like to generate a region on the top of this normalized traveling wave background. And it turns out that it has been done before. So it's not a novelty what we are doing. In some sense, it's like a remake of a movie in black and white. We are remaking it in color version. So I would like to mention that it has been done, and we also put it up in Mikhail back in 1974 and has appeared in several works in other groups. But very recently, one year ago, two papers come simultaneously. Our paper with my students Anna and Mark. We were focusing on the obtaining the dispersive characteristics for these bridges, bright and the paper of the Synthesis was focused on creating similar solitary wave solutions by degenerations of more complicated algebraic geometric solutions, finite get solutions in the problem. So I'm going to talk a little bit about the details of how we can create bridges. We will use Darboux transformation. Darboux backward transformation, which is well elaborated to get n-soliton solutions and many other interesting solutions. But here we are thinking about Darboux transformation on the traveling wave background. So U is the traveling wave. And V naught is a solution of the Lax equation. And because the traveling solution has this very nice traveling wave coordinate, there is a separation of variables for the solution of the Lax equation, which is a paramount importance both for the existence of bridges as well as for the stability of the traveling wave background. The separation of variables with the profile being a solution of the spectral problem, yesterday we spoke of genus. Lamma equation, and the parameter omega here appears from the time evolution given by certain characteristics dimension. Now, what is the spectrum of the Lamma equation in this particular case of the traveling wave solution? It's a one gap potential. There is a finite band here, finite gap here, semi-infinite band, semi-infinite. We can use vector transformation with a particular solution of the Lamma equation for particular values of the eigenvalue lambda, spectral parameter lambda. And we can choose it either in the gaps or in the bands. If you choose in the bands, we will not get any interesting non-singular bounded solutions. But if we choose it in the gap, then we can add a solid spectrum. And we have two choices to have these parameters chosen in the same gap, in which case we will get bright regions, or in this narrow finite gap, for which we will have damage. And so, of course, we can only do it if we can solve the Lamma equation. And this is a classical theory that this equation can be solved in an explicit way in terms of elliptic functions. In fact, the solution is a quotient of two Jacobi functions, but not Jacobi elliptic functions as NC and Dm, but Jacobi theta functions. And the only thing I wanted to mention here is that the function h here, theta 1 function, is vanishing at the origin, and the function theta is strictly positive everywhere on the line. So the quotient is theta appearing to be in the denominator, it becomes a bounded nice expression, and the parameter alpha here is the root of the theta 1 functions. There are two linear independent solutions with either choice of the sign. It's important that this quotient of Jacobi elliptic functions, Jacobi theta functions, is multiplied by exponential. That is, z theta function, the theta function, which is a logarithmic derivative of the theta function, and it determines an important characteristics of the bridges. It determines localization of the solidums inside of the period. So what is particularly interesting about this representation is that we are supposed to find solutions for the values of lambda. That's not easy. It's not easy, but if we can introduce a very smart translational parameter here for the zero of the solution, then it becomes easy in a parametric form. So in other words, instead of spectral parameter lambda to be the dominant parameter of the problem, it's a translational parameter alpha becomes the dominant parameter. And lambda is uniquely defined in terms of alpha. And in fact, one can consider different values of lambda and find uniquely the values of alpha for each values of lambda. So in particular, if we look at this characteristic equation and pick lambda inside of the finite gap in the yellow and the blue dot, then the values of alpha goes along the real axis. So that is the real width of the solutions of the equation. If it goes inside of the band, then the direction of alpha goes vertical in the next direction. And if it goes below, then it goes horizontal again, but it is now misplaced by half period of the elliptic functions in the complex plane in the imaginary axis. So there is a one-to-one correspondence here from alpha to lambda, it's a parametric representation. And moreover, because of separation of variables, we can find omega very explicit way in terms of certain theta functions here, also parameterized uniquely in terms of alpha. So here in this formula, we have three main ingredients of bridges in both the localization width, the width of the solid, the speed of the solid propagated on the background, and also this translational parameter alpha, uniquely defined in terms of lambda, spectral parameter, it gives us the shift of the bridges relative to the So the only thing is that now we have two solutions. We take linear combinations of the two solutions. We take Darboux transformation. We claim that this will be the breezer on the top of the traveling wave here, but we have to worry whether the Darboux transformation become boundary solutions of the singularity. And in fact, if we take lambda in the semi-infinite gap, then both solutions here are sign definite. That's a Sturm theorem for any solutions for any parameter of the Schrödinger operator below the bands. And the solution of the Schrödinger equation is sign definite. So if we take a positive linear combinations of positive definite solutions, we have no problem to use this Darboux transformation and get the bridger in a very nice way. So here it appears to be second logarithmic derivative of the Jacobi theta functions related with the Jacobi elliptic function Cn squared. And in this nice way, we can see that the tau function appears to be the sum of the two distinct versions of the theta functions, each multiplied by exponential function. So the shift, the localization, and the speed are all important formulas so that we can proceed with understanding characteristics of the in the finite gap, unfortunately, each solution has a zero because the alpha is real, H vanishes at the on the period games to zero. So there is no way to take a linear combinations of sign and definite solutions to get the sign definite function. Unfortunately. And however, we realize that in this case, we do the complex translations of the argument of the variable x to the half imaginary period, then we get bounded solutions. So this kind of a shift which we have seen on the alpha half period translations in the imaginary axis becomes important here to finally get bounded solutions for the other case when lambda is in the final gap and this is calculated. So all the information is encoded here. There are elliptic functions very explicitly parameterized for each of the parameters so that we can plot the final dispersive diagrams, the Shift parameter here normalized by the period. We can prove from elliptic functional representation that it's monotonically increasing. The localization parameter kappa monotonically decreasing. We can prove it in the same infinite gap. And then the speed parameter, we can prove that the speed is greater than the speed of the traveling wave. And the bridges looks exactly like this. The family of the bridges. Because the lambda is taken to the left, the larger is the shift. And the bigger is the amplitude, the bigger the speed, everything that's according to our understanding of such solutions. In the finite gap, we have here again monotonicity of the shift, but localization parameter has a maximum. And so for this maximum, for very particular values of lambda inside of the gap, we achieve the maximal localization of the regions. So if you look at these families of the dark bridges, they look like the depression profiles of the very background, then it's interesting to look what are the dark bridges in the cases of the maximum localization of the red blobs. And here you can see the black bridges, the black solitons. It's full effectively going through the zero limits. So in other words, this kind of constructions can be completed analytically by using double transformation and some tricks of the elliptic functions based on the solutions of the language. Before I go further, I would like to just do a detour. Yesterday, Peter Miller introduced the Benjamin equation. It's like a deep water theorem versus shallow water theorem. It's all very important equations of mathematics. In this equation, there is a simplification from a technical point of view. All periodic wave solutions are not elliptic functions. They are trigonometric functions. It's easy to play for applied mathematicians like myself. And this is representations of the traveling wave solutions, the complete family of traveling wave solutions. The Lax spectrum of this traveling wave solution has been obtained only very recently in the work of Gerard and Capella. They proved that there is a one band and semi-infinite band, exactly similar to the solutions of the Lambda equation, so that we have an option to think about AKNS solitons with lambda to the left of the left edge, or with lambda in the right. And in both cases, we would have bridges, and both bridges would look very different from each other. In the same infinite gap, it will be bright bridges, in the finite gap, it will be dark bridges. So before I will mention something about the constructions of the bridges, I would like to mention some important moments. That in the case of Benjamin equations, there are two remarkable discoveries. First, there is no phase shift of the soliton propagates along the background. It's identically equal to zero. Everything related to the algebraic solutions of integrable equations. Even they describe collisions of the solitons, no shifts. And that's the one problem. And the other property is astonishing that the speed of the bridge is exactly the same as with no background. So there is some kind of efficient separation between non-trivial periodic background and solitary propagation in the top. So if we will take zero background, it will be still the same solitary. Now, about the constructions of these bridges, it can be done very easily because all multi-periodic solutions are formulated in terms of elementary functions, and so one can get bridges without Darboux transformations. One can just do the same degenerations of the bands for the multi-periodic solutions, we include the points of eigenvalues. It's a well-known procedure for the long wave limit when parameters are 7 to 0. In this case, one can construct not just one family of bridges, but multi-soliton family of bridges. In particular, with two eigenvalues here, we can construct two solitons moving with a faster speed, bright, one soliton bright, one soliton dark, and then two dark interactions. So it's entire family of such bridge solutions can be described very efficiently in terms of elementary functions and this volume. Now, I promised a connection between existence of the bridges and the stability analysis. Remember that in the Lax equations, there is effective separation of variables for the graphing wave solutions. And this separate, okay, before I go this, in the separation of variables, there is a eigenvalue parameter omega, which is uniquely defined in terms of characteristic polynomial characterizing the traveling wave solution. It's a cubic polynomial, the coefficients of which are given in terms of the three parameters of the traveling wave. This is named from the compatibility condition of the lattice equation. But now, the important connection between the separation of variables and the stability analysis is that if we add a perturbation to the traveling wave diagram, we can also separate the variables in the framework of the linearization, linearized. And what is important that profile in the separation of variables is given uniquely in terms of the squared eigenfunctions. So if we have solutions of Lamé equation given by a bounded function, then it generates immediately solutions of the linearized KdV equation also as a bounded function. And the eigenvalue parameter lambda is just double of the eigenvalue parameter of the lattice equation. So if omega is uniquely defined in terms of the square root of characteristic polynomial, then we have immediately understanding what is the spectral bands in the stability plane by simply tracing the image of this I square root of characteristic polynomial. And in the case of Lamé equation, we know that the bands only exist between here, lambda 1 and lambda 2. Here, lambda 3 and infinity, and for all admissible values of lambda, the characteristic polynomial is positive. So that immediately the stability problem has purely imaginary spectrum. There is no eigenmodes which are growing exponentially in time, so that the traveling wave is spectrally stable. And so the existence of such Bridger solution stable propagations inside the gap is somehow related with the existence of the traveling wave being modulationally expected stable in the time. So that's a long introduction, I promised. And then in the rest of my talk, I would like to go over modified KdV equation. And I believe that this community thinks that modified KdV equation is exactly the same as a non-initial equation, very similar in terms of the studies. So, for example, focusing and defocusing modified KdV equation can be related with some focusing and defocusing analysis equation because they share the same spectral problem. They have different time values, but they share the same spectral problem. The main objective of my talk is to tell you that it's not the case when you are thinking about traveling wave solution. Why? Because in the traveling wave, you have to introduce the wave speed and obtain the profiles. When you obtain the profiles, you have two integration constants, two integrations here. And all traveling waves for the non-initial equation would correspond to the zero waves. So modified KdV equation has a more complicated family of traveling waves compared to the non-initial equation. And this parameter B is irreducible because there is only one transformation left. For KdV, we have Galilean and we have scaling. For modified, it's only scaling transformations. There is no Galilean transformation. There is no Lorentz transformation, which is available for non-initial equation according to Aristotle. But no such things was modified. And therefore, we can only reduce one parameter, but we are left with classes. And we have to separate the case when B is 0. That's the case when the traveling waves are the same as for the NLS. In the focusing case, given in terms of the S and functions. And the case when B is non-zero, when the solution is still elliptic, but it is represented in a much more function. To understand this is the best way to understand all possible periodic solutions of the problem is just to plot the orbits from space to. In the focusing case, we have several families of periodic orbits inside the quadratic curve. The generalized D-type solutions of analysis. The orbits outside of the homogeneous orbits. The generalized CN solution in the analysis case. And then for the defocusing case, there is only one family inside of the homogeneous orbit, generalized second SN solutions. The endless equation. Nevertheless, the whole machinery of integrability holds true for modified equation. In particular, we can still use the separation of variable and understand the admissible values of omega from solutions of the equation in terms of the characteristic polynomial here. It's now like quadratic polynomial muted by parameters with sixth order symmetrically here. And the Lax spectrum is again the same as the Fourier spectrum. It's a set of all admissible values for which you have a bounded quasi-periodic problem. Now, this polynomial P is quite important for the applications to bridges, offsets, and applications for the stability. First, roots of the polynomials are only related with periodic and anti-periodic solutions. And moreover, for the roots of this polynomial, we can represent the wave profile in terms of the sum of the squared eigenfunctions for the two values. And this representation formula is particularly useful if we are to find all solutions of the Lax systems for these particular values of the roots of this polynomial. And then finally, the stability analysis, because of separation of variables, the perturbations which satisfy linearized multiplication can also obtain in separated form, and they exist at squared eigenfunction relations. All solutions of the Lax equation determine profiles of the eigenfunctions of the linearized relation. And again, the square root of the characteristic polynomial becomes important for the stability analysis. So with this, let me give you an example of the stability in the simplest of all possible cases, the focusing case. In this case, the spectrum, the Lax spectrum is purely real because the operator is self-adjoint. All the roots of this polynomial are real. And in the general non-symmetric case, we have periodic wave solutions associated with the three gates. So some kind of generation of genus two solutions instead of genus one solution. And the Lax spectrum is located in between the roots for which the polynomial is still positive, so that the wave periodic wave is modulation and spectrum state. If we look at the focusing case, then the situation becomes more complex because the operator is not self-adjoint, and moreover, the roots are now complex stated. Compared to the pictures I saw in Jim's talk and Tamara's talk, I always like to rotate the spectral parameter so that the real parts of the synthesis becomes the imaginary parts of the synthesis rotation by 90 degrees. And now the outcome of this Lax spectrum and stability analysis depends on the periodic solution we pick. Inside the Hamiltonian orbit, which is a generalization of the DN solutions, the roots are all real here, and the bands are located at the real axis. And if you look at the admissible values of polynomial P and theta, then these are all positive, so that again we have modulation stability. That's my interpretation of the Katz modulus formed by KdV equation to get the solid and transmitted to the DN background or modified KdV equation for which it is stable. This, if it would be full numerical simulations for the focus and analyze equation, it makes no sense to consider interactions because the DN background is modulation unstable, but for the modified KdV equation, it is modulation stable. That was about the orbits inside the Hamiltonian loop. So in fact, inside of each of the Hamiltonian loops, there is no difference in stability analysis of the left loop and the right loop, surprising outcome of integrability of the system. But if we look at the periodic orbits outside of the Hamiltonian orbit, then the roots of the polynomials becomes complex. And there is one band along the real axis, which is still mapped on the imaginary axis, but there are two symmetric bands in the complex plane, which are mapped in figure 8. So that the CN solution is in fact modulation and spectrally unstable. And it doesn't matter which orbit I pick, there could be differences in the Lax spectrum, like different interconnection, but still no difference in the outcome of the modulation stability analysis. They are going to be stable. Related to this, there will be a difference whether we have bridges or rock waves on the top of this periodic background. And this has been a joke about 5 years ago, together with Jim Chen from NG. We have been developing a technique to construct peregrine type solutions from non-trivial periodic backgrounds from the roots of this polynomial, and by using this kind of squared eigenfunction relation that the periodic profile is given by the sum of the squared eigenfunctions. So with this, we can characterize all solutions of the Lax equation for the roots of the polynomial. One solution is bounded, either periodic or anti-periodic. The other solution is unbounded, growing. So that if we use a Darboux transformation with unbounded solutions, we get a non-trivial row plane. And the beauty of the focusing case, that's a focusing case, that the Darboux transformation is never singular. If all solutions here are real values, then there is no singularity here, and we get the bounded solution here. But it depends on the choice of the root. It is related to the choice of the periodic form. So here is the with three real roots, no type solutions inside of the commutative orbits. For each root, we can use this Darboux transformation to construct a gradient. And the gradient comes from infinity, goes to infinity, and propagates like this sort of array. There are three very particular speeds of the gradients, which are associated with the roots of this polynomial with the band ages. And this can be constructed. What I want is more. I want to have the ability to construct eigenfunctions of the Lax equation in between the roots, so that I can generalize this algebraic bridges to the full exponential range. And at this point, you are not able to do it. And now, in comparison, if we now look at the periodic wave outside of the commutative orbits, with the complex roots here, then one root is still real. It's a pair of roots, it's still real. So we can use Darboux transformation to generate algebraic region here. However, there is a pair of quadruplet of complex roots for which the one-fold transformation doesn't return real value solutions. So the only hope to get real value solutions is to do the two-fold transformation and pick up the roots in complex conjugate pairs. The two-fold transformation looks harder, it's more difficult, but it is also bounded, no singularities of its denominator, and it gives us a row plane solution. So as a result, we can see that in the case of instability, we have appearance of just row plates. In the case of stability, for the previous example, we have no row plates, but only algebraic reasons.
Question.
Yes, yes.
Where, when you do the Darboux transformation, where are you placing the point?
When I do the Darboux transformation, I place it exactly at the root. So whatever we can do here, whatever we have achieved in this paper, was done just for the roots of the polynomial thing. And the roots are this red cross.
Where's the branch?
Right in the branch. And the third part of my talk will be to think about if we can construct homogeneous solutions of the Lax equation in between the branch points, so that we will be able to generalize this kind of thing.
Because you put it there.
Yes, that's the algebraic idea.
And if you put it inside, it will be it's of one. So
Exactly. Like exponential. Okay, so this closes my second section, and I'm left with only one section for which I'm going to raise this question whether we can obtain an explicit elliptic functional representations of the eigenfunctions in between the branch points, and whether we can use them to construct bridges. And to simplify it, I'm going to focus from now on the defocusing modified integration. So a quick recap is that in the defocusing case, there is only one family of traveling periodic orbits. The Shabbat or AKNS spectral problem is self-adjoint. There are three parameters here in the family, and the family is available in analytical way in this form, but doesn't help me to find an explicit analytical expressions for the eigenfunctions. And the spectrum here is purely real with the three layers in the full case. We know that it's modulation stable, so it makes sense to raise the question that the bridges exist and the bridges dark or bright, thin bridges. And in fact, the status of things at this point is that in the case of symmetry being zero, when the traveling wave is the same as for the analysis, we were able to construct bridges in explicit form. Surprisingly, it's not the same form as the one people observed for the analysis situation. It's more complicated and extended, but we were able to do it. It's a success story. And in the non-symmetric case, it's still a work in progress, and it's very anti-dimensional. So the success story for BB0 is the availability of the explicit formulas obtained by Smirnov and other people 30 years ago. We have drafted these formulas from more recent papers of Takahashi. And they are given like in the case of Lamé equation, it's a quotient of Jacobi theta functions. This translational parameter here, there is an exponential factor with the parameters here very explicitly formulated in terms of translation parameter Z. And again, the Z is a nice, smart choice of parameterization because it parameterizes the spectral parameter. Compared to the KdV equation, so now it's symmetric case, we only have two gaps. Three gaps, and both gaps are symmetric, example, it's enough to consider just one gap. And when theta is chosen in this gap, then it is the same for the translation parameter to go along this length segment. So that it's a translation in imaginary axis by water. In the case it was half here it's a quarter. Nevertheless, we can translate it along the quarter period. It's a smart choice of parameter alpha. Everything is expressed uniquely in terms of Jacobi elliptic functions. And then we can run the Darboux transformation. But this is defocusing. And Darboux transformation is generally singular compared to defocusing. Also, the two solutions we get, they have zeros. Only quarter period translations. In order to construct Vries solutions, one needs to complete the library of elliptic functions with the relations for the quarter period translations. We were not able to find it, so some of the relations had to be proven from scratch and successfully we have proven quarter period translations, but still the singularity is still here. And we were very happy to understand after some time that half period translations of the solutions in complex plane still return valid solutions. So the same half period translation which worked for KdV in the case of done bridges, work here for modified KdV. And so this is the outcome of the main result. If the traveling wave solutions is the same is a quotient of Jacobi theta functions with zero here, the Vries solution is a quotient of Jacobi theta functions in a superposition of three functions. One is not shifted, one is shifted to one direction, left, one is shifted to the right, and it's shifted to another natural factor which hides this information about localization parameters, speed parameters of the bridges. And this is a formula very different from the formulas that taken for the bridges or not in shared information. So with this, we have the dark bridges propagated on the traveling ground. We have information again available very explicitly. The same features and KdV for the dark bridges, we have the maximum point for the integration parameter. And if we look at the bridges at the maximum point, you can see that they are more like electric, just like cycles, which jump jump. So this is quite a full success story in the case of BB0, but now I want more. Now I want to understand where the bridges can be constructed in a non-symmetric case. So with these three parameters, we want to construct solutions outside of BB0. And this form is not very good, it's not very useful. There is a better form which was developed by Anatoly Kamchatnev around 90s. The form which relates parameters of these traveling wave solutions is exactly the roots of the polynomial T here. And this is the better form because we have three parameters for the root, we have three parameters for the traveling wave solutions. And what can show that the convolution formula is not zero, conformation is invertible, very nice. But still, with this kind of representation, it is not so easy to find eigenfunctions of the Lax equation. So we have to use here a full elliptic theory, back to the works of Laser, Whittaker, Lamé, and others. And so in particular, in this case, if you look at this representation, we remember that Sn squared function is related with Weierstrass function. So what we have is a linear fractional transformation of the Weierstrass function. Moreover, it's known that the square profile is just a linear combination of Weierstrass functions. The derivative is a linear combination of Weierstrass functions shifted to certain locations of the poles of the elliptic functions. In the fundamental rectangle, obviously not on the real axis, otherwise the solution would be bad. But this gives us a theory to think that the elliptic solution can be written in a nice form as a quotient of the product of Jacobi theta functions shifted to the locations of the zeros in the numerator and poles in the unit. And for this particular elliptic solution, we can find exactly two poles in blue and two zeros in red. Either real or imaginary poles are always happening on the boundary of the rectangle after the contribution. So as a result, the optimal representations of these elliptic solutions we consider to be this, the quotient of the product of the elliptic functions. These parameters alpha for the poles, parameters beta for the roots. And in fact, all the previous parameters, like zeta1, zeta2, zeta3 here for the roots of the polynomials, can be uniquely expressed in terms of these parameters alpha and beta. And with this representation, it's pretty obvious that traveling wave solutions in the full modified KdV equation are not the same as traveling wave solutions for the endless equation, because for the endless equation it was a quotient of a single Jacobi theta functions, but in a modified KdV it's a quotient of the product. But then I want more. With this representation, I would like now to express solutions of these Lax equations in terms of elliptic functions. And one can follow the ideas established in the theory of the dynamic solutions. So think about the quotient of the components of the solution will be given by the quotient of the elliptic functions. And because the double poles for phi squared cancel the double poles of the phi prime squared, the quotients are also unique. So the poles are just disappearing. And so one can introduce all the roots of one numerator and all the roots of the other denominator. And this is the two sets of the roots. And prove that the roots of the first denominator cancel two of the roots of the first numerator, and the roots of the second numerator cancel two of the roots of the second numerator. These four complex parameters satisfy continuous derivation according to the elliptic theory, and with these four parameters we can introduce the representations of the solutions as a quotient of the product of Jacobi theta functions multiplied by the exponential, and everything can be uniquely expressed in terms of these translational parameters. That one starts at 2 star. It looks like a success story, but for a black mathematician like myself, it's not, because we only have one spectral parameter. I understand if there is one parameter Z for translation which uniquely parameterized parameter Z, but I don't understand how from this parameter Z I can find these four roots. And that's a problem. And if we look at the symmetric case, it's a similar quotient, but it was only two roots here, and only two roots there, and the two roots there were related with the two roots here. So as a result, there was a smart choice of introducing translation parameter Z as a parameterization of the spectral parameter. So it worked. But in the case of genus solutions, it is open. It is like get some kind of input from the expert in the audience. Maybe it can be closed. Maybe there will be some breakthrough in this direction. But so far, I finished with this slide, which shows numerically computed roots in just hyperbolic case. We found that the roots have a symmetry if theta is in the gaps. We only worry about regions in the gaps, therefore we don't need to worry about anything else. And so when theta is in the gaps, there is this symmetry reflection of the root of the cognitive functions about the imaginary axis. So there are 4 roots, 8 roots here, but only 4 roots make a story for the representation of the functions. So there are reflections here, but this gives us 4 real parameters, and with the completeness relation, we have 3 real parameters. So still not a unique representations in terms of zeta to define these roots. I want to know how to define these roots, and that's what stops us to finally compute the complete family of Riemann solutions for this very in modified equation. So to bring you to the summary of what I have been talking, I wanted to stress out that an integrable system is a very nice tool to study spectral stability problem by using straight eigenfunction relations. Black spectrum maybe cannot be found analytically, but it can be very well approximated numerically, from which the stability spectrum is obtained right away. And then by using elliptic theory, we can characterize slack spectrum and associate eigenfunctions in some cases, but so far not in all cases we want. And with this eigenfunctions, Jargo transformation, also the generation technique can be used to generate regions. Regions only available for the model, I mean, only relevant for the modulation stability and block waves in the case. Thank you very much for your attention.
You expressed the difference between NLS and KdV. When I went to the complex mKdV, the same as NLS again.
As a Hirota type equation with the complex.
Right, with a complex field, right? One square modules side.
We will have to look at the traveling and standing wave solutions if we are dealing with complex equation. And I think that there will be still the extra integration constant which can be described the failure of the traveling and standing wave solution. So there will be a constant when it is set to 0, it is the same as the ones. But when it's not 0, then it is also relevant for the elements, but it just gives you a different family of solutions. For example, this kind of traveling wave for modified KdV are relevant for the double periodic patterns in the analysis equation. The ones of things like Korteweg&ndash, it's a double periodic with respect to space and time variables. These are the solutions for which this constant is non-zero. So obviously the family of NLS is all somehow related with the family of modified KdV, but we have to distinguish what is the main object of the study. And so if traveling wave solution is the main object of the study, then the two families. But one is included.
In internal waves, the mKdV is usually a correction of the KdV. So I was just wondering, probably an easy answer. The focusing, defocusing, how do you do it? Like you've got 2 terms now, right? I mean, is it as easy of a?
It's a separate studies, focusing and defocusing.
Yeah, for you, but now you have 2 terms, right? So you have alpha u2x, plus alpha 1 u squared ux.
So you are talking about Gardner type
Yeah.
equation? Gardner. Thank you for this question. So in fact, this parameter B is 0 when we think about modified B equation. But when B is non-zero, that's more like Gardner equation, because we can use Galilean type transformation to get a shell, like in KdV equation, it was Galilean type transformation. Gradient transformation with a constant here. Just it's not invariant. For KdV equation, it was invariant. It moves one KdV to the same KdV. But for modified KdV, it maps modified KdV to the Garnier equation with quadratic and cubic nonlinearity. And because of that, what I was talking about for zero is some sense relevant for the full internal rate problems with the Garnier equation.
This is heavily, building on the integrability of the system.
Yeah.
So how would you extend this kind of ideas to non-integrable systems?
There have been several works when Breezer type solutions like Peregrine Breezers can be continued in non-integrable case, mostly numerically, obviously. When the parameter of non-integrability is small, it usually persists as a pattern, but when you deviate far from integrable cases, some solutions behave very strangely and maybe disappears. This kind of Breezer type structures disappears. So the beauty of integrable equation is that we can try to solve the problem exactly. But then this exact solution could be a seed for full hydrodynamical experiments, full fiber optic experiments, but it also can be a seed in a numerical continuations of the solutions in the
Yes, so you can do it for total lattice as well.
I'm not an experimentalist, so I don't know, but total lattice, yes, for total lattice, it should be done. Total lattice is very similar to the KdV equation, so I would anticipate that there will be a family of bright breezes, a family of dark breezes. They have to be discovered.
Okay, more questions?
So about this first part, you talked about this bright and dark breezes of KdV. I think it should be some easy physical interpretation why in one case it's in a band now in a gap is there, such interpretation. No, it's not necessarily.
I'm not so good physicist either to have this kind of interpretation. But yeah, that's maybe the next slide. That's one of the interpretations. The large amplitude gives you transmission, the small amplitude gives you absorption. And so there are two interesting cases which commonly happen in medical situations, in physical experiments. And with this, it's clear that if we now think about this background not to be a modulated traveling wave, but just a pure traveling wave with a constant parameter, there should be two families of solutions. To the left moving, that's the dark, and to the right moving, that's the bright. And then I didn't have any idea of how to look with these two families, and then a very strong feeling, intuition that bright which is associated with side with peak and singing in there, and dark is associated with that.
But then I guess physically you would need to pump some energy into this thing, right? To actually generate these waves, because you have oscillations ahead and behind the wave, right?
Why energy? It's just you have to start with a soliton. So there is a coherent structure like dispersive shock waves, and then in order to generate, you have to create a soliton. And then for the constant parameters, you have to create some kind of a impurity inside of the traveling wave. And then this impurity has to be of a right amplitude, right sign, so that it either propagates to the right as bright or to the left as dark.
Okay, more questions?
Yes.
So when I want to find out I analyze the 4 digit doing moments. Why you like to make it 6
Because of B. When B is 0, that, or maybe you're thinking about analysis.
modify. And then the 4 digit doing all, and why not to go to 6? Why you prefer to go to 6?
In some sense, I don't have a choice. I have to do what analysis tells me to do, and here, here, I think here, we can see that if I want traveling wave solutions in the broken situation, that's a B non-zero. So when B is zero, that's a heterogeneous connection. The solitary would be just hyperbolic 10, and then the periodic order is given by Sn functions. For this case, zeta 3 is 0. So by factoring out this, you will have important. But if B is non-zero and the symmetry is broken, all these values, which are the bandages, they are non-zero. So we don't this found from the separation of variables here.
1.6, never get the 6. Single one, right?
I think what Tamara said, you just look for traveling
Yeah.
solutions from the roots. But he's looking at the spectrum.
No, that's a spectral problem. That's a polynomial. That's a round polynomial. That's a the characteristic polynomial for the Lax equation. And you are talking about these. This is always point. No doubt. So there are 3 parameters in this quantity. And from these 3 parameters, I can define 3 parameters of the turning point. These are U1, U2, U3, U4 are roots of this vortex, which satisfies the completeness relation. So everything is done at this level, but it doesn't lead me to nowhere. It doesn't lead me to anywhere if I want to study the last.
Yeah, so in the first bullet of your conclusions, you were talking about the usefulness or stability of the Zaharov-Sabat problem effectively. So if people these days are using a lot the Zaharov-Sabat problem to study non-integrable problems, I'm just wondering if that connection to stability, or if you've thought about that connection to stability as you deviate from integrability.
By perturbation argument, if it's a small perturbation of integrable cases, and the linearized KdV will be also perturbations of the linearized integrable KdV, and then for the linearized integral KdV, it's a complete relation, and then you can look for the perturbative series to study to approximate eigenfunctions for the linearized non-integrable KdV. And I think here everything is nice because of Lacaze theorem. So we know what we are looking for, the set of admissible parameters for which the solutions are bounded, and the solutions are bounded in periodic, for periodic, and in between by using for periodic.
Let us start Dmitry again.